We have been talking about the discrete Fourier transform for a few lectures now. We talked about how the discrete Fourier transform is related to the discrete time Fourier transform. It's nothing but samples of the discrete time Fourier transform from 0 to 2 pi with an interval of 2 pi over n radians. And we looked at how you can use that information to do what's known as spectral analysis. We briefly talked about a number of aspects of spectral analysis that you should be familiar with. So that covers the discussion that we needed to have for the, the applications of discrete Fourier transform in terms of analyzing signals. If you get a signal, you are interested in finding out what kind of frequencies exist in that signal. We talked about how you can do that using the discrete Fourier transform. In today's lecture, we want to move to the aspect of how can discrete Fourier transform help us do processing of signals. So if we are given this situation that we have a input signal xn and we have a system hn, the impulse response, and yn is the output, we know that the input-output relation is simply given by convolution of the input with the impulse response if this is an LTR system. Now what we want to talk about is how can this convolution inside a digital system be implemented using the discrete Fourier transform. So that will be the goal of our discussion in this and the next lecture. How can the DFT help us do this convolution? And why we might be interested in this, it is because of computational complexity. So if you use the convolution formula directly, what ends up is that the computational complexity is pretty high. It's almost square in the number of length of the input samples. And what you want to do is use discrete Fourier transform to reduce that computational complexity. Now we talked about it briefly, the discrete Fourier transform itself, if you use the exact formula, it also has square complexity. It is pretty high complexity operation, but we talked about some sort of algorithms that help you do the DFT computations in a very fast manner. So we talked about that DFT can be computed in a fast manner using a class of algorithm. It's not just one algorithm, using what is known as the fast Fourier transform. Or as it is abbreviated, FFT. Okay? And the same goes for the inverse version. So in general, endpoint DFT typically requires order n squared. So this means n squared times some constant number mathematical operations. But what FFT does is reduces this complexity to almost linear in n. So FFT helps us compute endpoint DFT in order n log n to the base 2 operations. And because of this, you can do the FFT, you can do DFT computation in a much faster fashion. And effectively, that is the tool that we will use to argue that DFT can also be used to do linear convolution. Okay. But to understand that, we have to understand many properties of the DFT first. So what this lecture is about is properties of the DFT. Some are pretty general. You have seen similar kinds before, but there are a couple of properties that are unique to the discrete Fourier transform. They don't exist in any other transform. So we'll have that discussion. Okay. So the first property is the linearity property. So just like all the other transforms that we have studied, DFT is a linear transform. What this means is that if I have two pairs, Gn, and they are both n, we compute the endpoint DFT to get Gk, and we have a sequence Hn, and we compute the endpoint DFT to compute Hk. And of course, the implicit assumption in this discussion, at least, that I'm making is that if you are computing the endpoint DFTs of Gn and Hn, then Gn and Hn must satisfy one particular constraint. So the implicit assumption is that both Gn and Hn are finite length, and not only that, but their length is smaller than or equal to the n that we are using for computing the DFT. So n has to be greater than or equal to length of Gn and length of Hn. So if that is the case, it simply follows from the definition of the DFT. DFT involves only summation and multiplication. You can verify that if I give you a different sequence alpha Gn plus beta Hn, where alpha and beta are scalars, and I asked you to compute their endpoint DFT, then the DFT of that is simply the linear combination of the DFTs of individual sequences, alpha Gk plus beta Hk. Yeah. Now, it's a trivial exercise to verify that because Gn and Hn have length which is smaller than n, and the way we defined the length, the way we were defining the length was you start the sequence as 0. So if you have two sequences whose length is smaller than or equal to n and you add them up, this new sequence is guaranteed to have length less than or equal to n because of our assumption of the length of Gn and Hn. Right? So indeed, this is a well-defined operation that we have a length n sequence, we are computing its endpoint DFT. Now, be careful about the fact that this property only holds under the assumption that both the DFT sequences are endpoint. If you use, let's say, 10 points for one sequence and 20 points for another, then you cannot use this property. They have to have the same point length. Okay? The second property that we are going to study is very unique to the discrete Fourier transform. Okay? And that involves what's known as circular time shifting. So before we talk about this property in terms of the discrete Fourier transform, let's try to motivate this in a little bit non-rigorous fashion, but hopefully you'll get the idea. Okay? So Assume we are talking about a sequence which is finite length. So we have Gn of length less than or equal to n, and we have its dt ft g e to the j omega. Now, if I shift this sequence by some amount, right, let's say we shift Gn by amount n naught. So let's call that g of n minus n naught. Okay. What effect does it have on the discrete time Fourier transform? So what is the Fourier transform of Gn minus n naught, discrete time Fourier transform dtft? So the dtft of that is e to the minus j omega n naught, g of e to the j omega. And what is this thing? This is basically a phase shift of minus n naught to frequency omega. Right? So shifting in time creates a shift in phases of the frequencies. Now, you may be tempted to have a similar kind of a property for the discrete Fourier transform, but we have to be careful with that because we could get into trouble. When you shift the sequence, and the way we have defined the length of the sequence, when you shift the sequence under the definition of length of a sequence, what happens? So if we take the example of, let's say I have a Gn, which is a length 4 sequence. Okay. This is my Gn. It goes from n equal to 0, 1, 2, 3. And let's define my n to be 4. Okay. So I can compute the 4-point DFT of this. And now let's say I am interested in g of n minus 1. So just shift it by 1. What happens? That I have 0 at n equal to 0 now. I have n equal to 1 is 1, 2, 3, 4. So n equal to 2, 3, 4. Well, this shifted sequence, that means, according to the way we defined length, the length of this is now equal to 5. But when we are interested in doing DFT computations, we have to work with the same capital N. So if you originally started with some capital N, and if you are not careful, if you shift your sequence by too much, what will end up happening is you will end up with a different length sequence, and you now can't talk about the DFT with the same length. Okay, so for this Gn minus 1, you can't talk about, again, up to the context of this class, you can't really talk about 4-point DFT because it is now a length of 5 sequence. Okay. So this means that the property that we talked about here, this does not apply for DFT. Okay. Instead, we have to talk about something different. So this, to distinguish that, we will call this shift as a linear shift. Okay. But for a similar kind of a property in the discrete Fourier transform, we have to define something called circular shift. A circular shift is basically a shifting of your signal such that the new signal that you get has the same length as the signal that you started with. Okay. So before we describe the property, we'll define what we mean by circular shift. Circular shift mathematically is defined by this modulus operation. So we have this notation which is called K mod n. We talked about it earlier. This is defined as the smallest positive integer r such that k equals to n times q plus r. Okay? So it's effectively the remainder, but you have to be careful that we are only interested in sort of positive remainder. Right? So what this means is that if k is itself positive, then k mod n is simply equal to remainder of k divided by n. Okay? But if k is negative, then you have to define k mod n as capital N minus remainder of k divided by n. Of course, the remainder of k divided by n is always a number smaller than n, right? So if the remainder was sorry, it should be n plus. If the remainder was negative, then you will have n plus remainder of k divided by n. It will be a number smaller than n. Okay? So k mod n is always a smaller number than, so k mod n always is a number between 0 and n minus 1. Okay? So you can have k any number, but your output is always a number between 0 and n minus 1. Okay. So an example will be a few examples. For example, minus 1 mod 3. If you divide minus 1 by 3, of course, you get the remainder as minus 1. But so what we'll do is n plus the remainder. So 3 minus 1 is 2. Similarly, 3 mod 3 is 0. If k, of course, is itself between n and n minus 1, 0 and n minus 1, then k mod n is simply the same number. It is equal to k. So what happens is it's effectively this cyclic counting. If you do the mod operation on your integers, right? 0 mod n is 0 up to n minus 1, and then you start repeating that same sequence again. Okay, so if I just do it by a number line, I have 0, 1 up to n minus 1, then I have minus 1, minus 2, minus 3, and I do n and so forth, right? And if I just do, well, I'm going to do a mod operation on this by n, what happens? Up to n minus 1, I get back the same number. So I get at 0, I get 0, 1, up to n minus 1. But at n, what do I do? I get back 0 again. It's just a periodic repetition of the same sequence, right? What is n plus 1? That is 1. And I keep on doing that. For example, 2n minus 1 will be n minus 1. Similarly, if I go to the negative axis, I just repeat the same sequence again. So if you are ever in doubt what is minus 1 mod n, well, you have to do the same repetition here. So that will be actually n minus 1. Okay, and you keep on going up to this point. And so minus n will be 0. So when we take the mod operation, we always get back a number between 0 and n minus 1. We can't go outside that range. And based upon that, we can now define circular time shift can be defined as follows. By, for example, n naught, this is defined as g of n minus n naught mod n. Okay. So what happens is that when you do a circular time shift with mod n operation, this sequence has length capital N. So whereas when you do linear time shift, you get back a sequence which is of longer length. When you do a circular time shift, you get back the same sequence as the previous one. Because the only indices that are allowed inside, they range from 0, 1 up to n minus 1. So you can call this g tilde of n as this operation. Intuitively, you can say that this is circularly shifting Gn clockwise by n naught. So there are two ways that you can understand the circular time shift. One is you just plug in the values to get back what should be the answer. For example, say Gn is defined as n for n equal to 0, 1 up to n minus 1. So Gn looks like this. It's 0 at 0, 1 at 1, 2 at 2, and let's make it simple, precise, n equal to, let's say, 4. So 3 and 4. Okay. So this is my Gn. And I'm now asking, give me a new sequence g tilde of n, which is g of n minus 1 mod 4. So you are asking, give a new sequence which is circularly shifted by 1. Okay. So you can explicitly compute that. So what is G0? G tilde 0 is simply G of 0 minus 1 mod 4. That is G of minus 1 mod 4. That will be equal to, according to the definition we had, that will be G of 4 minus 1 equals to G of 3. Okay. And so G of 3 is simply defined as 3. So G tilde 0 is G of 3. So this, since capital N equals to 4, actually this should only go up to 3. So this is 3 is my capital N. Okay. Now G tilde 1 is, again, I can do this. I have 1 minus 1, 4. That is simply 0 mod 4. And as long as the number is between 0 and n minus 1, I get back the same number when I do the modulus operation. So I get back G0, which is 0. Let's do G tilde 2. That is G of 2 minus 1 mod 4. That is G of 1 mod 4. and 1 mod 4 is simply 1, so that's G1 equals to 1. And finally, G tilde 3 is equal to G of 3 minus 1 mod 4, that is 2 mod 4. Again, 2 is less than n minus 1, 2 is less than 3, I just get back G of 2, and that is 2. So the new sequence I get is, first of all, it is the same length. Circular shifting gives you the same length sequence. At n equal to 0, I get the value 3. At n equal to 1, I get 0. At n equal to 2, I get 1. At n equal to 3, I got 2. Okay. So if you actually look at, if you compare G tilde 1, which is circular, G tilde n, which is circular shift by 1, and Gn, what do you see? What has happened is that whatever was at, so it was circular shift by 1. So what happened was whatever was at n equal to 0, it moved to n equal to 1, as you do in linear shift. Whatever was at n equal to 1, it moved to n equal to 2. Whatever was at n equal to 2, it moved to n equal to 3. But the issue is that your capital N goes up to 3. So if I shift the little n equal to 3 point to the right, I get a number which is bigger than 3. So I'm not, in the circular shift world, I'm not allowed to go beyond the length n. So what do? I basically wrap that around. I still have n equal to 0 left. What I do is I actually, instead of moving the little n equal to 3 point further to the right, I actually move it to the 0th location. Right? So it's like the n equal to 3, it's like circularly connected to 0th location. And instead of going forward, I go back to 0. So what has happened is n equal to this point actually has gone to this location. Okay. And this operation then can be, we can graphically represent it a little better. So there is a graphical way of representing circular shift. So when you are doing circular shift, you shouldn't really think of a number line, you should think of a number circle. Okay. When we do linear shift, we have a number line and we shift everything to the right. In the world of circular shift, what we should think is we have a numbered circle with capital N spots. Okay. So I basically draw this circle where I have n equal to 0, n equal to 1. Right? It's like taking the linear line and just connecting it back to 0. I go n equal to 2, n equal to 3. I keep on going till I get n equal to n minus 1. So this is sort of my number line, but instead of a line, I have a numbered circle. And this is fixed. Okay. Now, what happened is that we were originally given a sequence. And for that, I will actually draw another circle. We were given a sequence which was G0 at index 0, G1 at index 1, G2 at index 2, G3 at index 3, and keep on going up to Gn minus 1. And circular shifting essentially means that this inner dial, right, if you think of these as two circles, the outer circle represents indices and you keep those fixed. This inner circle, circular shift, rotates this inner circle to the right or left depending upon whether your circular shift is, for example, n naught or minus n naught. Right? To the right or clockwise / left if we are given, for example, g of n minus n naught mod n, then you just rotate this by that amount. Okay, so what will happen, basically everything will sort of move n naught positions forward, but the moment you go above the range n minus 1, things will start coming back to 0. So if I rotated all of this by 1, right, G0 will, for example, go to 1, G1 will go to 2, G2 will go to 3, and Gn minus 1 will go to 0. And you can do that even if you had a shift of more than 1. If you had a shift, if you were given g of n plus 1, for example, mod n, then instead of going right, you will go left. Instead of going clockwise, you will go counterclockwise. So in that case, your whatever is at n equal to 0 will actually move to n minus 1 and so forth. Okay. So you can think of circular shift in that way. You can also think of circular shift on a linear line. So you could keep your plot of n equal to 0, for example, n equal to 1, up to n equal to n minus 1. Okay. And the idea is that if you are shifting things by n naught, all of the things get, instead of going forward, what you should think of is that this is virtually connected to n equal to 0. Okay, so this is effectively, I'm redrawing the previous picture, but now on a line. Right? This n equal to n minus 1 is connected to n equal to 0. So everything gets shifted to the right, and the moment something goes beyond n minus 1, it comes back to 0. And you just keep on doing this operation. Okay? Now, of course, if you were to do this operation counterclockwise, then you will actually connect n equal to 0 to n minus 1. This figure that I have drawn, there is no standard way of doing that. For example, your text has it the other way. Your text actually has the sequences in the indices in the counterclockwise direction, and so the inner dial, you always rotate it in the direction of the sequence. I just find this more intuitive than the way your text draws it. So your text has the outer circle in this form. It has n equal to 0 and then n equal to 1, n equal to 2, and it goes up to n equal to n minus 1. But if you are doing circular shifting by, let's say, 1, then you have to, if you follow the text example, then you have to rotate the inner dial counterclockwise. But I don't find that as intuitive as just taking the number line and just turning it into a circle. Okay. So the main point is, regardless of whether you do circular shift using the circular shift or the mod formula explicitly, or you do it using this graphical representation, the main point is that circular shift results in the same length sequence as you started with. So if I'm given Gn is of length n, then I circular shift that by n naught. That is also of length n. And we can now talk about the endpoint DFT of both the sequences because both are length n sequences. So the property of circular shift is that if you are given Gn and you have endpoint DFT to get G of k, and now you circular shift it by n naught, and you compute the endpoint DFT, then you see the operation that we talked about earlier, which is that you get e to the minus j 2 pi k n naught over n, gk. Okay. Each coefficient of your DFT undergoes a phase shift proportional to this expression. So this is like the DTFT formula. The difference is that instead of linear shift, you have the circular shift, and instead of e to the minus j omega n naught, because what is the interpretation of DFT? It is samples of the DTFT at 2 pi k over n. So your little omega is effectively 2 pi k over n, and you have the phase shift at that frequency. Okay. The third property is then very similar. If we understand what is the meaning of circular shift, then that is circular frequency shifting. Again, it's analogous to the DTFT world. We know that if we multiply a time domain signal with a complex sinusoid, then at least in the DTFT world, your DTFT gets shifted to the location of that sinusoid. You have this shifting of the frequencies. In the world of DFT, what you have is if you multiply your sequence Gn with e to the j 2 pi k naught over n times n. So you multiply it with this is a complex sinusoid of frequency 2 pi k naught over capital N. So k naught is a fixed number, and the assumption is Gn is of finite length. So you compute the endpoint DFT. What happens at the output is that you have a circular shifting of your DFT sequence. So you get k minus k naught mod n. Okay, it's the dual of your circular time shift property. When you circularly shifted your time, you got a phase shift. You got multiplication by e to the minus j 2 pi k over n n naught. When you multiply your time sequence with e to the j 2 pi k naught over n times n, you get a circular shifting of your DFT sequence. Okay. And then there is the duality property, which is something that you have seen in all transforms, but again, the difference will be that we have to be careful about this circular shifting aspect. Okay? So the duality says that if I'm given Gn and its endpoint DFT is Gk, and now I actually use my DFT sequence as a time domain sequence. So this is capital Gn, and I compute the endpoint DFT. Now I can do that because when I take the endpoint DFT, Gk is a length n sequence. So what happens is that you get capital N due to the scaling times G of minus K mod N. Okay. And just to remind you, you can simplify this further. This will be equal to N G of N minus K just by the definition of this mod operation, and N G0 for K equal to 0. So 0 mod N is 0, but minus, for example, K mod N is N minus K. So these four properties are nice if you are doing some sort of analysis. They are also helpful in some other context, but will after this property will study the most important property of the discrete Fourier transform, which is called the circular convolution. So we are now going to start discussing about one of the most important properties of the discrete Fourier transform, which helps us use it for computational purposes of linear time invariant systems. So that property is called the circular convolution property. And just like the circular time shift, before we can describe that property, we need to understand what does the circular convolution mean. Okay. So unlike linear convolution, which can be defined between any two sequences, they can be infinite length. For our purposes, we are going to define circular convolution to be between two finite length sequences. So that's a theme that always exists when you are doing DFT based analysis. You are working with finite length sequences. And why? Because you are interested in using them inside digital systems where you are forced to work with finite length sequences. And just like the DFT, you need some number to define circular convolution. So again, linear convolution, you can just say two sequences, compute linear convolution. If I have two sequences for circular convolution, I need to say what is the length of the circular convolution. So the setup is similar to DFT. Let's say we have number one, a sequence Gn is of length, let's say N1, and Hn is of length N2. We'll say compute circular convolution of length capital N, and the assumption is that capital N is greater than or equal to max of N1 and N2. Okay. So the length of the circular convolution, you will want that to be greater than or equal to the length of either one of the two sequences. Okay. And that is setup that we have seen earlier too. And there are many ways of writing the circular convolution. You could write it, for example, Gn circle, you put the number inside Hn, which means circular convolution of length n. Okay. You could also, some people will also write it as Gn, use a convolution operation but put a circle around it. Okay. Hn. In this case, you have to specify the length explicitly. This notation basically makes it easy for you to know its circular convolution and the length of the circular convolution you're talking about. This notation, you have to specify the length explicitly. Okay. So what is the formula for linear convolution? We know that it's yn equal to gn convolution with hn. That is simply equal to m from minus infinity to infinity, g of m, h of n minus m. That's the general formula. Let's assume that n1 equals n2 equals to capital N, just for the sake of argument. Well, in that case, although the linear convolution formula is m from minus infinity to infinity, I can actually, because this gm in that case is equal to 0 for all m not in 0, 1 up to n minus 1. So if I say my G is a finite length sequence, there is no point of having the summation go from minus infinity to infinity. I can simply say m goes from 0 to n minus 1, G of m, h of n minus m. And this is yn. Now in this case, we all know that if you convolve two sequences of length n, their linear convolution, the length of the linear convolution, that length is always greater than the length of both the sequences. In fact, you can write the formula that length of yn, the linear convolution, so it's equal to length of gn plus length of hn minus 1. In this case, where I'm making n1 equal to n2 equal to n, that is equal to 2n minus 1. So my yn exists for n equal to 0, 1 up to 2n minus 2. So we want to talk about, and then in the DTFT world, we know what is the relationship between the linear convolution and the discrete time Fourier transform of the sequences. We know that if Gn has Fourier transform Ge to the j omega, and Hn has Fourier transform of He to the j omega, then what is the Fourier transform of Yn in terms of the two Fourier transforms? So y of e to the j omega in that case is Ge to the j omega, h of e to the j omega. Okay. This is of course something that we already know. What is the purpose of this discussion? That we want something similar in the world of DFT. We say we have one sequence, you compute its DFT, you get another sequence, you compute its DFT, and somehow we want to say that we multiply the DFTs of those two sequences and we get something similar to linear convolution. But just like the argument we made for circular shift, we cannot explicitly get linear convolution. Why? Because when you linearly convolve two sequences, you get back a sequence whose length is much bigger than the length of either one of the two sequences. In the DFT world, in the DFT computation, we are forced to work with that whatever operations we do, we don't change the length of the sequences. Okay? So that's where circular convolution come into play. We will define a new sort of convolution, which is that the length of the convolution is the same as the length of both the sequences. Okay? And the way you define circular convolution is very similar to this expression. So remember this linear convolution expression for finite length sequences. What does linear convolution is doing? Linear convolution it says fix, at least the way it is written, fix G, flip H, and then linearly shift H. Linearly shift the flipped H. So that is what linear convolution graphically means, right? You fix one sequence, flip the other, and then slide it or shift it. Now, fixing part is fine, but the way we'll define circular convolution is do a slight change in the formula. We'll define in the following way. We'll call yc of n just to make it clear that circular convolution. The first part, the summation will remain the same. It will be m from 0 to n minus 1. We'll have gm. Okay. The trouble is with this shifting operation, because this shifting operation is effectively what is responsible for taking the length of the n sequence larger than the length of hn or gn. So what we'll do is, instead of doing this linear flip and linear shift, what we will do is have this mod operation, n minus m mod n. Okay. So you just compare the two. Here we have simply h of n minus m. Here we have n minus m mod n. And we'll look at it more carefully in the next class, but the meaning of circular convolution is exactly the same as linear convolution with a few caveats. So the first part is same, fix G. Okay? And just like the linear convolution, I can change the roles of G and H. It's commutative. So fix G. Now linear convolution says flip the other function. In the circular world, we'll say circularly flip H. Okay? And what does circular flip means? Basically, circular flip means this. This is circular flip. We'll look at it explicitly what it looks like. Whereas simple flip is h of minus m, right? So, and then for each, if you want to compute your output at little n, in the linear world, what you do is you linearly shift the flipped version. What we have to do in circular convolution is circularly shift h of minus mn. So how do we circularly shift that? Which is that h of n minus m mod n. That's the circular shift operation. So it is very similar to linear convolution with the caveat that all linear operations, linear flip gets replaced by circular flip, and linear shift gets replaced by circular shift. And we will look at it in more detail in the next class, both graphically and the tabular form, very similar to what you have done for linear convolution.